try to evaluate the scattering cross section from the analysis what we have done. Okay, what we have calculated? So we have this psi plus of x, the scattered wave. 24. Okay. In the forward direction. Is that true? So the psi plus of x we have calculated. That is in the form of. So we have considered an incident wave. So incident particle because that is along the direction. It is for I k z. Then we have written as it is for I k r by r, a spherical outgoing wave, and k prime. So this we have already derived in the last lecture. And what is this f of k prime? So that's actually equal to minus m by 2 pi s square probably. 23 x prime. It is minus I k prime dot of x prime, and then u of x prime. Okay, and what we have here? So some x prime and psi plus y. Is this a formula we have calculated last time? Okay, this is the correct formula we have derived here last time. So this is our scattering wave. So it contains, so this is our incident part and this is the scatter. So this I can write this psi plus s, psi plus of x as the psi incident plus psi scatter. Okay, so now let's calculate the incident current density because I have to calculate the scattering differential scattering cross section. Okay. So for calculating the differential scattering cross section, what I need to calculate? So the ratio of the outgoing flux to the incoming flux. Okay? So for that matter, if I need to calculate what is the outgoing flux, I need to calculate what is the outgoing current density, is it? And similarly, if I need to calculate what is the incoming flux, so I need to calculate the incoming current density. Okay, so let's calculate the incoming current density that I. Okay, so that's right. I'll use J because I usually we use as this iota. So Ji means the incoming current density. Okay. So I am having this equal to so H cross by twice Im. Since we are considering the massive particles, that's why M is there. So massive means containing mass, not M equal to 0. So it is simply psi star of incident, okay, gradient of psi incident, okay, then minus gradient of psi star incident and psi incident. Clear? Got it? Okay. So what is our incident? So I have used C here, incident. Okay. So what is our incident wave? So our incident wave is a plane wave moving in the z direction. V raised for I k z. So this is our incident wave. Now let's calculate this gradient psi will be what? Only partial by partial z. Because gradient is a vector quantity, it gives you the direction. Clear? So if I calculate now this gradient of psi incident, so it means simply z unit vector partial by partial z e raised for I k z. What it gives me? It gives me I k along the z direction. E raised for I k z. Clear? So this is very important. So now let's calculate it. So from here it will be minus I k z, minus and minus is plus. It will be twice I k, 2 and 2I will go. So it will be simply J incident will be simply H cross K by M along the Z direction. Now tell me what is the flux along the Z direction? Flux will be simply you take the dot product with the Z axis. Clear? Since I am considering my wave moving along the Z direction, so the incoming flux is simply, let's say, G dot B. Okay. So flux is same as the current density, but flux is a scalar quantity, and current is a vector quantity. To remove the vector nature, so I have put it along the z direction because I am considering the motion along the z direction. Now let's go to the outgoing current density. What's our outgoing wave? So outgoing wave are scattered. I will use psi scatter. So that's e raised to I k r by r f k k prime. So this is our scattered part of the wave. Clear? So now let's calculate the scattered current density. So are the outgoing. So let's write out. So J out, what that will be? H cross by twice I m. So you are having this psi scatter. Same formula. Okay. So what I will use? So I will use this way. So psi scatter. Okay. I will not use the formula again. It is e raised for minus I k r by r. So it is f star k k prime. Clear? The conjugate psi star. The first thing. Then what you are having? So gradient. So gradient. I have, since it's a spherical wave, so I have to use gradient in spherical polar coordinates. Clear? So since this only depends on r, I need to take only the r component of the gradient. So how much is that? So it is simply 1 by r, the unit vector, no sorry, it's simply unit vector r partial by partial r acting on psi. What is psi? E raised for I k r by r, okay, f k k. So this does not depend on r, so you can take it out. So minus, then you are having minus, okay, gradient, so it is r, okay, partial by partial r star of actually this thing, I k r by r, okay, f star k k prime, okay. So this is the first term. Then psi scattered, that is e raised for I k r by r, f k k prime. Clear? Everybody followed it? Okay, good. So now you can take, okay, so you are having this f, you take it out of the derivative because it does not depend on r. So f star is mod of f square. Same is from this very term. You take mod of f square out. So what you are having? H cross mod of f k k prime square by twice I m. Okay, so now what you have to do? So you have to differentiate it. So you need to differentiate this thing and add the terms, because once you different, it will be I k, it will be minus I k, minus and minus will be plus. So there will be something. So let me write the result. Okay. So it will be something h cross. So k will come out. Okay, and there will be some twice I m. Okay, divided by r square, because once you differentiate 1 by r square, sorry, one differentiation of 1 by r is 1 by r square minus 1 by r square. Okay, so you are having twice I m k, so they will cancel out, and there will be this direction. So r unit vector is there. So what you get? So you get simply h cross k by m, clear, mod of f of k k prime mod square r square. So unit vector. So this is the outgoing current. Clear? So now you are having, it is a radial current. Suppose you think of a sphere of radius r. So now the current moving through that sphere is radial in direction. So it moves along the radius of the sphere. Clear? Okay. So now I need to calculate what is the flux. So flux, for that matter, suppose you choose a sphere of radius r, let's say. Okay. So once you calculate the flux, I need to calculate the flux to small area. Okay, so let's consider this ds. Okay, so the ds is the element of the area of this very sphere, because if I calculate the flux means you consider the area, a portion of the area of that very sphere. Clear? Okay, so what is now the outgoing flux? So it will be simply j dot out dot ds. Clear? Got it? Okay. So now when you are having r dot ds, so it is something like this. Okay, h cross by 2m mod of fk prime square by r square. So it is r dot ds. Can any of you tell me what this r dot ds gives me?
Del omega.
So how we write the solid angle?
Omega.
In terms of this element of the area ds, because ultimately scattering will be through that solid angle. If you remember, we have that angular current density, clear, through some solid angle omega, clear. So if I am considering the small element of area of this surface, so it is a small solid angle d omega here, clear. So how much is that in terms of this? Yes, good. So we are having usually this d omega is how much? Anybody? ds by r square. It is actually r dot ds by r square. So that is same as magnitude of this thing. So it implies ds is how much? R square d omega. Clear? So now let's write it here. So the outgoing flux is, so it will be simply, now this r square and this r square will cancel out. So it is simply h cross k by m, 2m rather. So mod of f of k prime square d omega. Okay? Got it? Okay. So therefore I can write now my differential cross section. How we define it now? So the outgoing flux divided by incoming flux. So the outgoing flux, so we can write it like this in d sigma by d omega. So the number of particles per unit area moving, scattered number of particles per unit area divided by number of incoming particles per unit time. Clear? Or the outgoing current through that volume element d omega. Got it? So this I can put it this way: d omega is equal to, what is the outgoing flux? So it is, so it means actually the ratio of the flux through the volume element d omega. Got it? Okay. So h cross k, so it is mod of f k prime square, okay, divided by twice m. So there is d omega as well, divided by, so the incoming flux is h cross k by 2. So what does it mean? So it means your differential scattering cross section. So it is simply equal to mod of. Now look how simple the formula is. That's why this f of k omega is known as scattering amplitude. Clear? So because it is multiplying the factor e raised power I k r by r. E raised power I k r by r is an outgoing spherical wave, and a term multiplying that will give simply the amplitude of that wave. Clear? So now, or in other words, we can call that as a scattering amplitude. The differential cross section of a given process will be simply magnitude square of this amplitude square. Clear? Or the scattering amplitude. This scattering amplitude is very important in our analysis. Okay, so that means in a given process, if you know the scattering amplitude, what you know? You know differential cross section. From differential cross section, you can calculate the total cross section. Okay. So what is the total cross section? So it is simply you integrate over volume this thing. Okay, d sigma by d omega. So that is same as d omega mod of. Clear? Okay. So any question till now? So now let's go to an example. Yes. So before having a calculation, let's look at this f. So f k k prime. Let's look at this very formula. What is that? M by 2 pi h cross is it square. So you are having this d3 of x prime e raised to power minus I k k prime dot x prime. Then what you are having v of x prime, and then you are having x psi or psi plus of x. Got it? So this is our scattering amplitude of a given process. Now look here, this if I need to figure out the differential cross section of a given process, I need to find what this scattering amplitude is. Okay? For that matter, what I need? So I need to calculate this very integral, but this integral contains a term that depends on the psi plus. Clear? What is psi plus? Psi plus gives you the outgoing wave. Clear? So this which has actually the terms containing both incident wave as well as the scattering wave. Psi plus is like this. This psi plus of x. Okay. So we are having e raised for I k z plus e raised for I k by r f of k phi. Okay. So that means it depends on these terms again. Huh? So it is in this case it's very difficult to calculate. Okay. So how to do it? What I will assume, so there is a very important approximation here. I will assume this potential is not strong enough, clear? Such that this overlap I can represent by a free wave, free particle. Okay, so in order to give the glimpse of where exactly this approximation comes from, so it comes from this very series. Suppose if you are in, we wrote the solution of the Schrodinger equation psi in terms of this very operator. E minus h naught plus minus I epsilon v psi, okay, plus phi. And phi is our incident wave. So phi is a wave when your particle is free. Okay. So when v tends to 0, your solution is phi. That means free particle completely, no scattering at all. Now if I have to solve this very equation, what I need to do? In order to figure out this psi on left hand side, so I also need to know what is the psi on the right hand side, is it? So it is some sort of a transcendental equation. I need to solve it by iteration, in a recursive fashion, in such a way that the magnitude of this term is very small. This v, if the potential is small, then I can make a perturbative extension like this way. Okay, so let's substitute the value of psi here. I know what is the value of psi. It is this objective. I can put this psi here. Okay, so like this way. So in the first like this way. So I will keep phi there. This is our phi. Then I am having this objective e minus h naught plus minus I epsilon v. For psi, what I will use? I will use this expression. So it is v phi. Okay, phi plus 1 divided by e minus h naught plus minus I epsilon v psi. Clear? The way we have done the Dyson sum, if you remember. Okay. So it is simply the perturbative extension. Okay. So you are making a recursive nature of the equation. Okay. So it is simply phi plus what you have got here. E minus h naught plus minus I epsilon v acting on phi plus the terms like, okay. So you are having 1 divided by this operator h naught plus minus I epsilon v, then you are having this operator, okay, plus minus I v psi. Okay, now, so this is the 0th order term, this is actually the first order term, okay, and this is actually second order term. You are having v square term here, clear? So that means up to the first approximation, so you are having this v psi, you can replace it by what? V phi. That's exactly happening here. Okay? Okay, if you pick only one term from that very expansion, it will give you this term exactly, replace this x psi plus as x phi. Clear? So if you are having this kind of replacement is there, so it will go as simply x phi. Clear? So if you put, let's say, x on this side, so it will be x phi, then x v phi. So you can insert the completeness condition, you will get again what? X phi. Clear? You got my point? Okay. So that means if you are replacing this term by this term, okay, so we call this approximation as the Born approximation. Got it? And that is known as actually the Born series. Okay. So we are having the Born or the first Born approximation. Everybody followed it? Okay. So let me write it. Okay. Okay. So let me write it this way. So I have given actually the idea where from actually it comes. Huh? So what I am saying, so ultimately what you are solving, the first question is that what you are solving. You are solving actually a Schrodinger equation. Okay. For that you have actually arrived at a solution of this form. Clear? Now in this solution, what you need to know? Psi. Psi is unknown to us. But if you look at the right hand side, psi again appears. So how to solve this thing? So there is an approximation if this v is small, if the magnitude of these terms are small. Okay, in other words, so I can actually make a recursive make use of the recursion such that I will expand this expansion in a perturbative fashion. Okay, what I mean by that, let's take this psi, keep this psi as such, and replace this psi by this complete expression. Okay, so it is then I arrived at this kind of series. Now look at this term. So when you take v tends to 0 again, so you get psi back to 5. Clear? But when v is not 0, but it is small, so you have got what here? V phi. So what was the term here? V psi. Okay, so this is the 0th order term. Up to the first order approximation, my V psi I can replace it by what? V phi. Okay, so if you go to the second order correction, then put actually psi again this formula. What you write? So V phi will be okay. So V psi will be again replaced by V phi. Okay, but you will be having two V phi's. So in other words, you will be having V squared kind of term here. Okay, so this will be actually the second order correction. So now let me write this approximation in this fashion. Okay, so if the scatter is not strong, then we may infer that it is not a bad approximation. To replace this x prime psi plus by x prime phi. So we call this as the Born approximation. So that means what I am doing. So x prime this psi plus. So it is x prime. In one more formula where we started, we have put x. You put it as an x prime because there is an integration over x prime. So it's x prime. So it goes simply as this x prime phi. So this I can write as e raised to I k x prime. Clear? So simply a plane wave. Huh? Okay, but what is the momentum here? Momentum is actually k, but this is a plane wave at which point? X prime. Got it? So that x prime is a point where it's within the scattering region. Got it? In that region, you are approximating it by a plane wave. Okay, but there is an integration; it will give a different effect. Okay. So therefore, I can write this f. So in the first Born approximation, I will put 1. Okay, so this is simply the perturbative expansion. Okay, so I will write this. The first Born. So this is known as first Born approximation. That's why I have put like this thing minus 2 by h cross square. So it is d3 of x prime e raised power minus I k prime dot x prime. So it is e raised power I k dot of x prime. So I'll behind this x prime. Okay. So how much is that? So it's minus m divided by 2 pi h cross square d3. So it is x prime. X prime. So it's e raised power I k minus k prime dot of x prime via x prime. If you see, this is simply the Fourier transform of potential, this object. So in the first Born approximation, the scattering amplitude is given by the Fourier transform of the potential. Okay. Potential. Okay. Now you can replace this x prime by x because it's a dummy variable. Huh? Okay. So got it. So everybody. Now let's take the examples. Huh? A profound example. Okay, so before doing that, so let's make a remark about the if we are having potential is spherically symmetric. So how this looks like. Okay, suppose if you are having spherically symmetric potential. Okay, you can replace this x by r as well. Huh? So r means okay, r will give you the coordinate. So this formula you can, this is valid for d dimensions as well. You can instead of 3 you can use d here. Got it? So this formula is valid for d dimensions as well. There is no problem. So then you can evaluate actually d dimensional integral. Okay? So you can put this is true for one dimensions as well. Huh? So this kind of formula. That means all dimensions it's okay. Huh? So now let's look at the spherical potential. So what we mean by the spherically symmetric potential? Okay. So now let's look at on which factor this scattering amplitude depends on. Okay. So let me draw these two vectors. So you are having a vector k, and then you are having a vector k prime. Clear? So let's assume they are making an angle theta. Okay, so if you are having a spherically symmetric potential, the scattering amplitude should depend only on the theta. Clear? Okay. So that's what we are going to show. So now what is your k prime? K minus k prime. So it's some. So this is your q. That q vector defines k minus k prime. Clear? Got it? Okay. So now let's take that exponent of this magnitude of this thing. So k minus k prime kind of thing. So what does it mean? It is simply equal to magnitude of vector q. So let's call that as q. So q is okay. So you can think q is actually the difference of these two vectors. Okay. So now let's take the square of this thing. So what will be the square of this thing? It will be the magnitude of this thing. So it is k square plus k prime square minus twice k prime cosine of theta. Got it? Now since we are in the elastic scattering domain, we are considering only the elastic scattering, or at least we are considering the energy conservation. When you are having an energy conservation, this k magnitude of k and magnitude of k prime is same. Okay? So we are having k magnitude of k and magnitude of k prime, that is same. Let's call this. So due to energy conservation of the process. So that I can write therefore this. So it will be twice k square. It will be twice k square. That comes out. So it's 1 minus cosine of theta. So that's actually 4 k square sine square theta by 2. Okay? Everybody? Okay. So now let's take this formula. Okay, so this very integral. So therefore I can write this f of 1. Yes. So for spherically symmetric potentials, now on which factor it will depend? On theta. So I'll write f1 of theta as minus m by 2 pi h cross square. So now let's evaluate this integral. So it will be 0 to infinity. So it will be r square dr. Clear? Okay, then sine of theta d theta from 0 to pi. Then it will be what? 0 to 2 pi d phi. Okay? So then you are having this very part, e raised power I. Since this is q, we have defined it by q. So it will be simply magnitude of q. Okay? So x prime cosine of theta, sorry, r, because we are using now it as r. So it will be r Okay, magnitude of x prime is r. Okay, so V of r. Okay, so now since there is no phi dependence, you integrate out phi, so that will give me 2 pi. Okay, so you are having minus m by 2 pi extra square. So you are having 2 pi coming from the phi integration. Now, okay, yes, everybody is following it?
Yes, sir.
Okay, so it is 0 to infinity. So dr r square, this thing. Now you are, okay, so let me write V of r here. Now you are having integration over theta.
Yes, sir.
So this factor depends on theta. This we have done in the last lecture as well. You put qr cos theta is equal to something. It will be simply e raised power I qr minus e raised power minus I qr divided by I qr. Clear? Got it? So everybody followed it?
Yes, sir.
So this is a simple integration. So r, 1r and 1r will go. So what you get? So by the way, memorize this formula. You should memorize this formula in the first Born approximation. So this is an important formula. Memorize it. So it is f1 of theta. So what it gives me? So let's make it sine of qr. So it will be simply equal to minus 2m by extra square q integration 0 to infinity dr r square sine of qr. Okay. Sorry, not r square, only r. So here. So this is the Born amplitude for what potential is? Spherically symmetric potential. Clear? Got it?
Yes, sir.
Any problem? So this should be also memorized because for a quick objective you will get use of this in there. So you need to simply consider whether the potential is spherically symmetric or not. Apply this formula. Okay, so let's take the example. Let's take the example of Yukawa potential. Scattering off by a Yukawa potential. So Yukawa potential, we know it is simply the screening Coulomb potential. Okay, so if you simply write the Coulomb potential, this is a Fourier transform. Clear? Okay, so if you write simply the Coulomb potential V of r is equal to 1 by r kind of thing. Okay, so it's very difficult to. Okay, so you will not be able to calculate that integral for this 1 by r. It will diverge. Okay, so now let's look at. Since this is spherical symmetric potential, what you get? So V of r is 1 by r. Clear? So r and r cancel. What remains? Sine of q. What are the limits? So it is a divergent quantity. So for that one, because the Coulomb potential is actually the long range potential. Okay, so you need to screen this Coulomb potential. Clear? Such that this integral converges. Okay, for that matter we will use the Yukawa potential. So let me write the strength of the Yukawa potential V naught. Okay, e raised power minus mu r divided by mu. While mu defines, okay, so V naught is the strength of potential and mu defines actually the range of the potential. Clear? So that means it is screened. So now for mu r larger than 1, so this will go to 0. Okay, so this will abruptly go to 0 for mu r larger than 1. Clear? So solution. So when r reaches mu, or in other words, when r reaches 1 by mu, so that means the range of the potential. Okay. So I should put 1 by mu gives you the range of the potential. Okay. When it reaches to the range, beyond that range, it drops sharply to 0. Okay. Got it? Abruptly, it goes like this and goes to 0. Clear? Everybody followed it? Now when you take that limit, let's say if you take mu tends to 0, forget about this mu. When you take mu tends to 0, what you should get? You should get actually 1 by r. So there is a 1 by r factor, I'm sorry. So you should get 1 by r. So let's forget about this mu. So if you put mu equal to 0, you get actually 1 by r. And V naught V will be simply Q charge. Yeah? Okay. So now when you take mu tends to 0, then this ratio must be fixed. Got it? So otherwise if you take mu tends to 0, this will diverge. Yeah? Okay, so this ratio must be fixed. Clear? So it will simply give the charge. Okay, in that case. Okay, so now let's calculate. Let's plug in this value here. Okay, so therefore our f1 of theta in this case it's equal to minus 2m by h cross square cube. So what you are having v of r, it's v naught divided by mu 0 to infinity dr r sine of qr. So it is e raised for minus mu r divided by r. Okay, so r and r cancels. So it's minus twice m v naught divided by mu h cross square cube. Okay, it is the integral 0 to infinity dr sine of qr a raised for minus mu r. How you can evaluate this thing? So this integral I can represent like this thing. I'll simply write this integral 0 to infinity dr e raised for I qr e raised for minus mu r and take its imaginary part. Because if you take the imaginary part, what you'll get? Sine. Clear? So what is the imaginary part? Okay, so what is the value of this integral? Let's put, so it will be 1 divided by mu minus I cube. Is it? What is the value? So you take minus out. What you are having? Mu minus I cube. So what is it? So is that a minus sign here? Minus 1 by, okay, minus 1 divided by mu minus I cube. Clear? So what will be now the imaginary part? It will be simply q divided by mu square plus mu square. Okay. So what is your this f of f1 of theta? So it is simply equal to minus twice m by, okay, so this q and that q will cancel out, extra square. So I will put v naught by mu here. So what you are saying? 1 divided by mu square plus mu square. Okay, so now let's put, okay. Okay, everybody followed it? Okay, so now let's calculate the differential cross section. So therefore d sigma by d omega, that's equal to, so it is 2m b naught by h cross square mu whole square. Okay, then you are having 1 divided by mu square plus mu square whole square. So this is your differential cross section area. Yes? Any problem? Okay. Now we know this, what is q? We have just calculated for spherical cylindrical potential. Q square is equal to twice q square into 1 minus cosine of theta. That is actually 4 sine square theta by 2. Clear? So now let's substitute it here. So you are having d sigma by d omega v naught by h cross square mu whole square. Okay, 1 divided by q square is actually equal to twice k square into 1 minus cos of theta plus then you are having and you are having whole square. Okay. So, okay, so now let's take mu tends to 0. Huh? So when I take mu tends to 0, what I told you? So this is, okay, so now from here you have to calculate. Okay, so let's have the home assignment here. Calculate the total scattering cross section. That means d omega d sigma by d omega. Clear? So it is over the solid angle. Now it depends on the theta. Clear? So what you are having? You are having an integral 1 divided by some theta cos square theta plus mu square theta kind of thing. Okay? Summation. So okay, so let me write. So it will be simply twice m v naught by h cross square mu whole square. Okay, so this integration will be sine of theta d theta from 0 to pi, 0 to 2 pi d pi. It is a solid angle. Okay, then 1 divided by twice k square into 1 minus cos of theta Yes,
Plus mu square.
plus mu square. Okay, whole square. So just evaluate. So this will be 2 pi will come out. Then you have to integrate out. You put cos theta equal to some z. So it will be something 1 minus z plus mu square. Just evaluate this integral. It is simple integral. Just do it. Got it?
Yes, sir.
So that will give you the total scattering cross section. Okay. Now let's make an approximation. Let's look at when the range becomes infinity. That means the unscreened Coulomb potential. So let's say if I am taking mu tends to 0. So what does it mean? So I am going to the Coulomb regime. Okay, not the Yukawa or the screened Coulomb potential. It is unscreened. Okay. So unscreened Coulomb potential. So we need to fix here V naught by mu is to be fixed. Okay. So this should have a fixed value. Clear? So let me use that value to be equal to ZE. So it is, let's say ZE is the charge of the incoming particle. Clear? So because ultimately it is the charge with which a particle interacts with a Coulomb field. Clear? So let's take ZE. Z is an integer. Okay, multiplied by ZE prime. Okay, or Z prime. Okay, let's write Z prime E. Or Z prime. Sorry. Z prime E. Z prime E is, let's say, the charge of the scatter, and ZE is actually the charge of the incoming particle. Clear? Okay, got it? So I will use this V naught by mu like this thing. Okay, so that means, okay, so this factor is taken care of. Okay, so this V naught by mu. So I have put it as Z prime E square. Okay, so let's put mu square equal to 0 here. Got it? Okay. So therefore I can write this d sigma by d omega as twice m by h cross square whole square. Then you are having this V naught by mu. So that is actually equal to Z prime E square. Okay, there is a whole square kind of thing. Okay, 1 divided by what you are having here. So twice k square into 1 minus cos theta whole square. Clear? So it will be simply 4 k raised power 4. Okay, so 1 minus cos of theta whole square. Okay, so it is what? Sine square theta by 2. It will be sine raised power 4. And there is what? A factor of 2. Okay, 2 to 4, it is 16. Okay, so it is something like, let me write twice m whole square like this thing. Z prime E square whole square divided by h cross raised power 4. So it's 1 divided by 16. Okay, k raised power 4 sine raised power 4 theta by 2. If you see, it's actually the Rutherford formula. Let's write it in terms of the incoming kinetic energy. So let's write E kinetic as h cross square E square by 2m. So let's use this very formula. So let's use this k in terms of the kinetic energy, then it will be easier. Okay, so which gives you d sigma by d omega. So that's simply equals 1 divided by 16 z prime E square by E kinetic whole square. Okay, 1 divided by sine raised power 4. So this is your Rutherford, well-known Rutherford scattering, Rutherford formula for Coulomb scattering. Clear? Got it? Okay. So let's stop here. 6 minutes.